I have the midpoint formula written up here. This is just straight out of your textbook. To find the x values, you have point A and point B. And point A, you would just take the x values, add them together, and divide by 2. That's how you find a midpoint. And then you take the two y values of A and B, add them together, and find the y value of the midpoint. That's it for midpoint formula. This formula, I believe, is given on the formula sheet of the IB exam, so it's not one you need to memorize, but we do need to know how to apply it. So if I give you the points A and B and it says they lie on the diameter of a circle, that means point A is going to be, here it says like -3, 5, somewhere over here. Point B would be the exact opposite, 0, 7 diameter. So we want to find the midpoint, which is going to give us the center of that circle. All right, that's the idea for example 1 here. So you do the x values, -3 plus 0 divided by 2. The y values, 5 plus 7 divided by 2. And that's how we'd find the midpoint. And we'll just call it point C for center. And we end up getting -3/2, comma, 12/2, which is 6. So -3/2, comma, 6. That's our first example of chapter 4. Hopefully a little bit easier than what we've been dealing with calculus. Hopefully. All right, so now here's where we're going to learn something a little bit new for this module. Three-dimensional space. Hopefully you've seen this before, a three-dimensional graph. But when we want to draw a three-dimensional graph, we kind of draw the z-axis. This is going to be our third dimension up top. And then we draw the x and y on the ground. So that's what this image is showing in the yellow box here. And we'll go ahead and label x, y, and z. And let's see, so this is saying in a three-dimensional space, the location of any point A is determined by an ordered triple of coordinates, so 3 points. All right. And each coordinate determines the location along the x, y, and z axes respectively. So whenever you see 3 points, like if it's 3, 2, 1, that's your x, y, z coordinates. That's kind of the new thing that we're going to be learning this module that'll be a little different than 2D geometry. Locating a third point, a point that's somewhere in space. And this shows like point A here, that's at the point x, y, z. All right, that's the idea there. Now, now for this next one, it's example 2 here. Even though we have a 3D point there, example 2 is actually still working in 2D here. It's saying that we're finding the values of x if the midpoint is -3, 1.5. So basically we're saying we have our x coordinates and we know it's -1 plus x divided by 2. That's equal to -3. The other one would be 10 plus 5 divided by 2 equals 1.5. That would be the idea to find the values of x if the midpoint is between 5 and 10, something like that. Okay, so now, just looking at this, I'm seeing 10 plus 5 divided by 2 should be 7.5, so I want to make sure I didn't type this in incorrectly when I put this problem in our sheet. Okay. So we do this, -1 plus x is -3. So to solve for x, what we're going to want to do is we're going to want to multiply both sides by 2. And that's going to get us -1 plus x equals -6. And then from there we would add 1 to both sides, and we're going to get x equals -5. Okay. It's really funny here is because I pulled this example out of your textbook, and the y values don't make sense because it'd be 10 plus 5 is 15 over 2, which would be 7.5 equals 1.5, which is obviously not possible. So that's actually a typo in your textbook. Let's see. Yeah, and it is between the points 10 and 5. Halfway between 5 and 10 is 7.5, not 1.5. So that's kind of weird. So what I want you guys to do is go ahead and, if you have your textbook with you, go ahead and change that to a 7.5. We'll just rewrite that in our textbook for chapter 4, example 2. So rewrite that in your textbook so you have the appropriate number there, since that y value is definitely incorrect. All right. Okay. So that's example 2. Example 3, this is when we're going to start looking into 3D spaces here. So it says a cuboid, which is basically, it's just a cube, and it's got the points A, B, C, and O, and then A1, B1, C1, and O1. And it says what the total dimensions are, 4 by 5 by 2. And then the vertices of the base of the cube have the following coordinates. So first thing we want to do is we want to sketch this graph. So we'll go ahead and create our XYZ sketch. And our point A is at 4, 0, 0. So that's going to be on the x-axis. And then our point B is at 4, 5, 0. So that's going to be on that XY axis only. So that's how we would kind of sketch that. Our point C is at 0, 5, 0. So the Y is at 5. And then it says point D, that should be point O. Is at the origin, which is probably why it's O. That's 0, 0, 0. So there's our cube, or the base of our cube. And now it's saying the area is 4 by 5 by 2. So this distance is 4, this distance is, let me change the color here. This distance is 4, this distance is 5, which means the height has to be the 2. So, for example, O1, which would be the point directly above this, would be 0, 0, 2. And all of the corresponding points would be straight up. So A1, for example, would be 4, 0, 2. We would just move everything up 2 units. And the reason I know it's moving up 2 units, again, is because the dimensions we're given is 4 times by 5 by 2. And we already know the width is 4 here, and the length is 5. So that means the height has to be the 2 to represent that volume accurately. That means I can sketch a B1 here, and I can sketch a C1, which is going to be 0, 5, 2. And then this B1 will move out here. It's 4, 5, 2. Okay, that's how we would determine the coordinates of B1, A1, O1, and C1. Okay, that's how we would do 3D graphing. Little bit different than our 2D graphing, but same general principles. We're just adding a new axis now, so that could be a little bit tricky. And now, once we have this drawing, it says, hey, let's go ahead and identify the midpoint of AC1. So the midpoint, we'll do in red here, going from C1 diagonally across to A. So A, for example, is at 4, 0, 0. C1 is at 0, 5, 2. So those would be our 2 points. If I want to find the midpoint of that, I'm just going to do the x's added together, the y's added together divided by 2, and then the z's added together divided by 2. So remember, it's x, y, z, x1, y1, z1, x2, y2, z2. And those are interchangeable. You could have them written the other way, because we're adding them together and then dividing by 2. So if we're looking for AC1, we'll start with the x values, 4 plus 0 divided by 2. And then the y values, 5 plus 0 divided by 2. The z value is 2 plus 0 divided by 2. That's how we would find our diagonals. So I think the hard part about these types of problems is just trying to get it set up and then go ahead and calculate those points. But the hard part might be the setup and trying to visualize what it's asking exactly. And for this one, AC1, we end up getting 4 divided by 2, so that's a 2. We get a 5 divided by 2, that's 5 halves. And we get a 2 divided by 2, that's a 1. Now we could have it as 2.5, that's perfectly fine if you're at 2.5 instead of 5 halves. 2.5 might actually be a little easier to understand, but there's the midpoint. Should be the exact center of the cube, theoretically. All right. And then the last one asks, what happens if we go from A1 to C? Would we get the exact same midpoint? What do you guys think? Would we get the same midpoint for part C?
Well, I mean, ideally, if we calculated the midpoint correctly.
Yeah, we'd get the same one, right? So the short answer is yes. And we can prove this by finding the midpoint. Finding the other midpoint, yeah. ideally it should be the same, right? We found the exact center of the cube, or the cuboid, so we'd want to find the exact same midpoint. All right, so same exact thing, okay? That's the idea there for problem 3. So yeah, we can prove it, okay? So for these types of problems, like example A, it might not be a bad idea to get some graph paper and sketch these on a graph. That might make it a little bit easier for you. You can just use regular grid paper to do that, to draw your X, Y, and Z axes. You can draw your Z and Y like a normal XY graph, but then you just draw your X diagonally coming out of it. Okay, that's probably the easiest way if you have graph paper available. Not a bad way to sketch it. Or you can sketch it by hand like what I did on the white here, which is perfectly fine. You can always import a graph if you're doing it on your device into this thing too. All right, so a few different ways to possibly do that. All right, so yeah, it should hopefully be the same point. We can prove it by finding the other midpoint. I'm not going to do that right now, but that's the idea. All right, last problem today. That was all midpoint formulas. We looked at midpoint formulas in 2D graphs, midpoint formulas in 3D graphs. Now we're going to talk about the distance formula, distance between 2 points. And distance formula is another one that would be given to you on the IB exam. So it'd be, in this case, you take the 2 points and you subtract them and then square them. And then we take the square root of the sum of all of those points. That'll give us the total distance. All right, and again, given to you on the IB exam, here's the distance formula right here. And example 4 says, here's a storage box. And it's got the sides O, C, D, R, and then F, B, A, Q. All right, the vertex A is shown at 2, 3, 4, and O is clearly the origin down here at 0, 0, 0. So it says go ahead and label R, C, B, and Q. R, C, B, and Q. So go ahead and see if you guys can label those points there. Okay, R, C, B, and Q. Take a minute and label those. Take a look at these points here. So we can tell that at point A, the X value is 2. So R should be 2, 0, 0. The Y value is 3. So C should be 0, 3, 0. B is directly above it, so that's only going to change the Z value. And then Q is directly above R, so that should only change the Z value. So 2, 0, 4. All right. So this is a box that's going to be storing our tools. So we need to find the maximum length of a tool that can fit inside the storage box. So that's going to be a point that goes from like either R to B or O to A. It would be one of those points. So for example, if we did from point O, that's 0, 0, 0, to point A, that's 2, 3, 4. That'd probably be the easiest one to do, because then you're just going to do 2 plus, you'll do 2 minus 0 squared. And then you'll do, let's do this. We'll say AO, the square root of 2 minus 0 squared, plus 3 minus 0 squared, plus 4 minus 0 squared. That's how we'd set something up for the maximum length. And then that's going to give us 4 plus 9 plus 16. 2 squared plus 3 squared plus 4 squared. And we should get the square root of 29 there. And then we can just turn that into a decimal. Square root of 25 is 5. Square root of 36 is 6. So it's going to be somewhere between 5 and 6. If I turn it into a decimal, just use my calculator, I think it's going to be like 5.4 meters if we round to the nearest tenth. That's how we'd find the distance between 2 points. And then it asks us for the height RQ of the storage box. This one is pretty self-explanatory because it's height. We're just saying what's the distance between R and Q, and that's a distance of 4. But we can still prove it algebraically by using the distance formula, because the coordinates of R and Q are both going to be 2. So we do 2 minus 2 squared. The y coordinates are 0. So it's going to be 0 minus 0 squared. And then the z coordinates are going to be 4. So it's going to be 4 minus 0 squared. So what happens is you're going to get 0 plus 0 plus 16. So you get square root of 16. And square root of 16 is 4. So for part C, when saying the height of the box, yes, I can show that that makes logical sense very quickly. But to show algebraically how to do it, we would still use that distance formula to prove it algebraically. That's the idea there. All right. And then the last part here says we want to find the angle between the diagonals BR and BQ. So the angle between the diagonals BR and BQ. And as we can see, those side lengths are drawn here. And then the angle's like right up here somewhere. It's going between that green line and the dashed green line in this drawing here. Okay. So in order to do that angle, what we need to know is we need to know a couple things. Right now we know that RQ is 4. We also know that BR is 5.4, or if we want to be more accurate, we can just say square root of 29 for right now. So when we want to do the angle, we could say sine. We could find BQ, but why find BQ when we have two sides? This is a sine function. We could do opposite over hypotenuse. So this is going deep back into the well of our SOHCAHTOA. So let's draw that triangle real quickly. This is side B, Q, and R. We know this is 4, and we know this is square root of 29. And we're looking for that angle right there, angle theta. So again, sine is opposite over hypotenuse. And Q is definitely a right angle, so sine theta equals 4 over square root of 29. And then does anyone remember how we find an angle? What do we use to get sine on the other side of the equation? That's a tricky one.
Did we just do like the inverse of sine?
Yeah, that's right. The inverse of sine. Sine inverse of 4 over square root of 29. And we just plug that into our calculator. And we will get, I don't know, 47 point something. 47.97 degrees. So it's safe to say that theta, when we round it, is 48.0 degrees. I'll put a 0.0 because that means we rounded it. All right, instead of saying that it's exactly 48 degrees. But yeah, so finding the angle between two diagonals, that's kind of like the deepest we're going, but that's prior knowledge as well. I think, again, the hardest part of these types of problems in 3D space is just trying to identify the picture. And it helps me to draw this picture right here So that way I can see what's going on. Okay, I just took that triangle out of the drawing up top here and redrew it down here, so in 2D space. So it makes it a little easier for me to visualize what I'm looking for. That's kind of the trick for this type of problem. So your assignment